Good evening, everybody. So, we will still continue with some of these aspects of reaction mechanisms in part 5, where we will mainly discuss about the fate of the molecules when it goes for certain type of reactions, particularly when we consider their electron transfer behavior when electrons are moving from one metal center to the other. So, what will happen in that particular case along with the other one, where we will find the different stereochemistry of these complexes can play some important role, such as in case of these cis and trans compound of this chloride complex of cobalt, where we have this 2 chlorine atoms to the cobalt center. So, out of the 6 positions, 2 of them are occupied by chlorine in cis geometry. When these 2 ethylene diamine groups bind to the cobalt in this particular fashion, and this one also gives us the corresponding trans geometry, where the cobalt center will show the corresponding binding of the chlorine atoms to the corresponding trans fashion. That means, we have a corresponding angle of Cl, Co, Cl in the range of, say, sometime is 178 degree to 180 degree. Here these 2 ethylene diamine chelating ligands remain in this particular fashion. So, when these 2 molecules basically react with some substitution, and if we just consider that one of these Cl atom is replaced by some other incoming group, that means this can go for the removal, that means this Cl can go out and some new group, say X minus, can enter and take the position of either this Cl or something is happening on the coordinate sphere of this particular environment. So, what basically goes for there, we can have 2 options from there. One is, if this particular center, if it is a center where we see that if we consider the corresponding charge neutralization by the ligands as well as the other chloride atoms, we find that this particular molecule is electroneutral. So, the oxidation number on the cobalt can be assigned as +2. So, this +2, so cobalt 2, that means 2 plus, and its corresponding radius will be greater than cobalt 3 plus radius. So, these are little bit higher, the atomic radius or the ionic radius for cobalt 2 plus will be higher than that of our cobalt 3 plus. So, when we go for these, we only expect that if the corresponding size of the atom which is present over there, which can accommodate something, that means our this Cl can go away and our incoming X is coming to attach to the cobalt center. So, this is one particular situation where our coordination number can be increased to 7, where these 2 bonds are pretty weak. One is going to decay or going to break, another is going to form. So, This we can consider at the corresponding dotted line for these longer bond distances with that of our cobalt X and cobalt Cl. And another situation which can have, which is based on the corresponding coordination number less than what we have here, because here the coordination number is 6, and here after removal of the Cl minus, so minus Cl minus, and this is plus X minus. So, we can have a situation where the coordination number is 5. So, a pentacoordinated intermediate we can assume is forming at this particular point, and how this pentacoordinated species can give rise to the product, that will tell us whether we have the different type of geometry where from we are starting our journey on the cis complex. So, it is a 5 coordinated intermediate which basically can in the next step can react with this X minus to give the corresponding product. And by analyzing the corresponding nature of this product, we consider that in case of cis geometry, that means when we start from the cis complex, the journey is going from completely from the cis compound, we get the retention of cis configuration. That means, when we have this particular intermediate, whether it can be a square pyramidal one or trigonal bipyramidal one, we find that the site where basically Cl has been removed is now simply occupied by the incoming X minus to give rise to the corresponding original configuration, that means the cis configuration, and it is not going for any other configuration like that of our trans one. So, these cis complexes, therefore, we can say that this basically responsible for retention of the corresponding cis geometry. So, this is one such example for these cis complexes of this cobalt, which can retain its corresponding cis geometry, that means no other form is forming over there. But what about the corresponding trans complex? In case of these trans complexes, the situation is completely different, because in this particular case it can isomerize, and how this isomerization can take place, that will depend on the spectator ligand, that means the ligand which is present, and depends on the geometry of the activated complex, that means the transition state. So, the ligands which are still present around the cobalt center, those ligands we are considering as the spectator ligands, and those spectator ligands, when they consider for the corresponding geometry, we can have again two different options, that means either it can be a square pyramidal one or a trigonal bipyramidal one. So, in case of this trans complex, what we find that isomerization will take place. Unlike the cis form, in this case the isomerization will take place and is dependent on the position in 3 dimension where y enters. So, now we will consider this as x is removing, we are removing x from the center. So, for the trans one, we have the ethylene diamine, and we consider these now as the presence of these 2 x groups. So, we will just see now this y will enter by replacing these x groups. So, the intermediate or the transition state what is forming it has a particular geometry, and that geometry is important if it has more than one positions to attack, where y can attack this particular geometry, and if it has more than one particular position, then depending upon these positions of attachment or position of attack to the cobalt center by y, forming new cobalt y bond, where we just deleted one of the cobalt x bond, that means it is again a 5 coordinated one. It is a 5 coordinate intermediate, and new cobalt y bond will form depending upon the intermediate geometry, and where from the y will enter the corresponding geometry. That means, in this particular step we have the 5 coordinated one, and is basically the corresponding addition of y, and y is added to give rise to the corresponding product. So, what we will see from there, so we have these situations. So, this particular one, if we have both of them as x, or one as a, another as x, so x will go and y will enter. So, how this cobalt x bond is being cleaved, that is important. So, when a trans geometry is present, that means these two ligands along this a cobalt x bond, which is close to 180 degrees. So, x removed, we get from an octahedral geometry a corresponding square pyramidal geometry, where A is forming the pyramidal side of the square plane forming by these 4 yellow orange spheres. So, these yellow orange spheres in this particular case are chelated by one ethylene diamine molecule, and here another ethylene diamine molecule. And then if y is again entering from that side where x has departed the molecule, x has left the molecule from that particular side, that means this particular side where we do not have any kind of reorganization of this thing. That means, this n cobalt bonds, the cobalt n, and this is another cobalt n bond along with this cobalt A bond, they are forming a T-shaped structure, but this T-shaped structure is not all the time very much stable until and unless we have a special stabilization for the square pyramidal geometry. Otherwise, these two, basically A and the nitrogen of this ethylene diamine, and A and the other part of the nitrogen of the ethylene diamine, they repel each other and they try to reorganize in a trigonal plane. But when it is not happening, that means this particular square plane, that means the cobalt N4 plane. So, when we have these, we basically see that this is the thing where we have these two nitrogens forming one such chelation, and this one is our A. So, this particular square plane has some extra stabilization, that is why these two bonds are not moving from this side to that side. So, this particular plane, if it is only a bis bidentate chelation, is not that we have something related to that of our porphyrin or corine type of macrocyclic coordination, where we know that all the 4 nitrogens are attached and we have a macrocyclic environment. In that particular case, the N4 ligand has some extra stability in a plane. So, it has extra stability in a square plane. So, that thing is also happening where we do not have this connection and we do not have this connection, is only ethylene diamine units present. So, this is our En and this is also our second En. So, the incoming y, so plus y, the situation incoming y will attack from this side and we get the corresponding retention of the configuration even for the trans compound that we are getting for the cis compound. So, this particular Y is coming from this side and attacking this particular cobalt center, giving the corresponding original compound where the geometry is same, only the position of X is now occupied by Y. But if the second thing is happening, that means some rearrangement is taking place between this particular plane, ANN plane, ANN plane, trigonal plane is rearranges, and rearranges means we should have sufficient flexibility for this bidentate chelation. This is the NN bidentate chelation, and this side also NN bidentate chelation. If we have little bit of flexibility for this rotation, we just basically get a trigonal bipyramidal geometry, where this ANN, this is the trigonal plane and this is the pyramidal side, first pyramidal side, and this is the second pyramidal side in the downside. So, now clearly we find that if we consider that we are not touching anything related to the bipyramidal part, that means these two nitrogens we are not touching, but within the trigonal plane, that means a triangle, this is a triangle. So, you have a triangular side. So, the triangle has three sides. So, it is side 1 when Y is attacking side 1, it is also giving the possibility, the second possibility. In second possibility, we have Y is attacking from side 2, this is the side, and this is the third possibility where Y is attacking from this side. So, when Y is attacking the cobalt center to get back the original octahedral structure, that means attack of Y will take place from this side, which is marked as site number 1, giving rise to the product, which is the same product with the change in X by Y only, which here we also get. That means the retention of configuration, that means the trans configuration of the complex. But if Y is attacking from site 2, that means from this side, and if it is attacking this side, this nitrogen is getting pushed to the transposition of A, that means towards the transposition of A. So, the nitrogen will come here and Y will take this particular position, which was originally occupied by the nitrogen of the ethylene diamine. So, we get one form where A and Y groups are in cis position. That means we have another form we are getting starting from the trans configuration, that a form which is a cis form. Similarly, we can attack from side 3, that means this side, that means between this A and nitrogen. So, between this nitrogen, so nitrogen again will be pushed towards this side and Y will try to take the position cis to A. So, like attack 2, here also Y will occupy a position where A and Y will remain in cis position towards this particular cobalt center. So, we get the corresponding cis configuration for this particular system. So, depending upon which particular side, depending upon the steric crowding and the size of this A and its electronic nature of this A, which is there, that means we are considering this as the corresponding spectator ligand. Depending upon this nature of A also, we get both the trans configuration as well as cis configuration if the attack of Y is equally probable from these three sites, that means site 1, site 2 and site 3, will get the corresponding two isomers, that means the trans and cis isomers in 1:2 ratio, that means one part of trans isomer and two parts of cis isomer will get. That is the thing, like other organic chemistry reactions will find that one of the isomer will be forming in excess compared to the other if the all three pathways, that means all three attacking sites are equally probable. So, that gives rise to the two forms where we can get the corresponding things, and next we will see how the typical isomerization reactions can take place. So, one particular part, that means if it is forming from completely one isomeric form to the other isomeric form. So, this isomerization reaction can give rise to similar to that of the substitution reactions. So far we were talking about a substitution of one particular group, that means the replacement of x by y. X is removing from the system first, then y is entering to the system. In a similar fashion, the isomerization of the molecules can also take place, where the substitution of the reactions are also similar to the corresponding isomerizations. So, one type of such thing can happen if we have a pseudo rotation type of thing, where Berry proposed this particular type of pseudo rotation, and Berry pseudo rotation mixes the axial and equatorial positions of 5 coordinated trigonal bipyramidal spaces. So, if we get straight away we get a complex which is intermediate, that means it is giving rise to the corresponding transition state for our discussion, where the geometry is trigonal bipyramid. And in this geometry we know that we have a typical triangular plane, and this triangular plane is responsible for giving 3 bonds, and these bonds are we consider as axial bonds. So, depending upon the nature of the donor atoms present over there, it can be nitrogen or it can be chlorine for this type of compound what we are discussing in this class, and the other one which is above the triangular plane, which is on the other side, that gives rise to the pyramidal structure of this. This is basically the corresponding one. This is axial, and this particular one, this is axial, and these 3 are equatorial. Which is in the axis, that means which is in the perpendicular position, which is axial, and in the plane, that means the basal plane what we have, they are the equatorial. Similarly, on the other side we have another axial bond on the other side of the trigonal pyramid. So, Berry proposes some kind of pseudo rotation of this, that means this particular geometry, this trigonal bipyramidal geometry can rearrange, and that gives rise to some situation where both square planar complexes which undergo associative mechanisms or octahedral complexes which undergo dissociative mechanism or intimate dissociative mechanisms involve a 5 coordinated state. If we get a 5 coordinate state, that means the 5 coordinate intermediate, then isomerization is possible from there. So, we have the octahedral complex gives rise to for a dissociative mechanism, that means one particular group is leaving the octahedral complex, giving rise to a 5 coordinate intermediate, and that 5 coordinated intermediate can undergo some isomerization reaction. So, we have this. So, this A means the corresponding axial bonds and E means their corresponding equatorial bonds. So, this is basically the corresponding trigonal bipyramidal geometry, and this trigonal bipyramidal geometry if we have, and if these two E moves from this side to that side, we get basically a typical square pyramidal geometry where this AE and this A and this E make the square plane. So, basically what we will be getting over there is something where we can consider these 3 are the corresponding bonds in the equatorial plane. These are the equatorial bonds. So, we label them, the donor atoms also are in the equatorial plane, and we have the axial one. So, this is one axial one and this is the second axial one. So, now what is happening over there due to this pseudo rotation? So, rotation can take place where originally what we have, this is close to 120 degree, all three angles, these three angles are close to 120 degree because we have a triangle, and if E is moving from this side and this E is moving, that means we try to increase this particular bond. So, due to that rotation, what is happening, this bond which is at also 120 degree can go for 180 degree. That means, this can go for straightaway this position, that means this E will go to this position, and as a result what we get from there is basically a structure like this, where this is the AA and this is the new positions of these two E. So, this E has moved, so and this is the other E. So, as a result what we are getting there is basically a square pyramidal one, where this is the square plane and this is the pyramidal side, where this one is forming. So, due to this rotation, a TBP geometry, which is this TBP geometry, is giving rise to a square pyramidal one, so this particular one. So, within this 5 coordinate species, which is also true for typical 5 coordinated compounds, they can have the different geometry and they can also undergo some kind of racemization or isomerization reaction due to this movement. So, once this group is forming, this can again further go for this kind of rotation along the same direction. So, what is happening then the next stage, that once these two E groups have been moved, we get this one, where we know the position of this E, this E, this E and these positions of A and A. Now, these two A groups are moving instead of these two A groups, because these two A groups have moved sufficiently and they reach to some equilibrium position. Now, once they reach to this position, these two A groups, these axial groups, so this particular one, so axial groups will start moving. So, pseudo rotation basically mixes the positions for these bonds, that means the axial bonds and equatorial bonds are no longer distinguishable once we have some intermediate structure. So, if we consider that, then if these are moving, that means this is basically this A cobalt A bond angle is 180 degree now, and if these two are moving, that means this A cobalt A bond angle will try to reach from again 180 to 120 degree. That means, these two will give us this 2A along with this E, which is in the pyramidal side, because these two E's are in a line along 180 degree, which is perpendicular to that. This E, I mean this A, this E and this A will next form a new triangular plane. So, a triangular plane is forming with this A, the other A, those two are moving, and the E which was originally present in the pyramidal side. So, we have E as the new trigonal plane, and E will still remain in the 180 degree side, will then therefore the corresponding pyramidal side. So, this will be below the trigonal pyramid plane, and this is above the pyramidal triangular plane. So, what is happening there? Therefore, from there we get something, some arrangement we will get where we will have a new triangular plane with two groups which are in the pyramidal side. So, these new groups will be presenting therefore as one as A, one as A, another as E also, and these E are the original E groups. So, basically what we find that we have moved from a situation where the starting molecule, say it can be the typical trigonal bipyramidal one, or it after dissociation of one group to this particular situation from the octahedral geometry, where we have all the equatorial groups are there and the axial groups are this side. So, we find therefore that very pseudo rotation can give us some situation where these axial bonds, the axial groups for the molecule, this is the start. We have started from this molecule and this is the end product. So, these two groups, these two axial groups which were present in the axial direction of the molecule. So, these axial groups will now go to the equatorial sides. These two A groups moving from here to here and is moving from here to here. So, axial groups have changed their positions to the new positions where they are occupying the equatorial positions. Similarly, these E groups which were present in this particular case, that means they were in the equatorial plane, one still this there, that is one of the E group still present in the equatorial positions, but two other. So, two other equatorial positions, say this position and this position, they are moving. So, this E is basically moving here and this A is moving here. So, these equatorial positions have now changed to the axial positions. So, this basically tells us that it is possible to mix the axial and equatorial position. So, we consider that axial and equatorial positions are mixed. So, this is basically the result of the very pseudo rotation. So, this can be considered as one kind of pseudo rotation where we get the change from this particular side to the other side. Now, we will consider that how we get the corresponding octahedral isomerization, where a different kind of twisting is taking place. So, what type of twisting we can have, that we see for this kind of isomerization reaction on octahedral molecules. So, where we see that the octahedral complexes can also possible to isomerization by a twist mechanism, unlike the very pseudo rotation what is forming for the 5 coordinated species, but in case of octahedral situation a different kind of twist mechanism is operating, and that twisting can give rise to the isomerization in octahedral complexes. So, how it takes place, that will see that it does not require loss of ligands, which is very interesting, that in previous cases we see that the octahedral complex is leaving one ligand giving rise to a pentacoordinated situation, and in that pentacoordinated situation we get a corresponding geometry of either a square pyramidal one or a trigonal bipyramidal one. But in this particular situation, the bidentate ligand, if they are present like acetyl acetone or ethylene diamine, they basically strictly attached to the metal center, they are not giving rise to any kind of bond breaking process, but they basically go for some twisted formation. So, depends on the energy barrier between the conformations. So, if we have one conformation on the left and other conformation on the right, and if the energy barrier is not very high, we can move from one barrier, crossing the barrier to one form to the other. So, it is Baylor who proposed the J.C. Baylor, the scientist J.C. Baylor proposed one kind of twist which is known as Baylor twist, is a particular type of twisting mechanism for this situation, where the pathway which can be taken away by the octahedral compound is that the racemization, that means 50% of goes from the one form and the other 50% for the other form, is via the formation of a trigonal prismatic intermediate. Because we know now that a typical octahedral geometry is nothing but a trigonal antiprismatic geometry. So, if that antiprismatic geometry can move to a prismatic intermediate with a D3H symmetry, the symmetry of the point group after the distortion is D3H, then we get something which is the result of the corresponding Baylor twist. Then another form of twisting is also possible, which is now known as this corresponding Ray-Datta twist. It is due to Priyaranjan Ray is there, and another is N.C. Datta, who they propose this twist, which is little bit different from this, but on the same line, but the twisting process is different. In this pathway, we get the corresponding formation of the intermediate, which is of lower symmetry compared to the D3H, it is of C2V point group symmetry. So, what we basically get out of these, that we have this triangular face, this octahedral triangular face we know, and in a stirred structure, in a stirred fashion, if this is bidentate one, all three are bidentate one, we get this as a corresponding trigonal antiprismatic structure. So, it is trigonal antiprism, because this is one particular triangular face of the prism and the back is the other one, which is equivalent to our corresponding octahedral geometry. So, when this movement is taking place, we get this antiprismatic one to a prismatic one. That means, if we just move these two planes, that means if we just move this point overlapping to this point overlapping to this, and this point overlapping to this. So, along this particular axis, which is our C3 axis. So, along this C3 axis, if the rotation is taking place, so that rotation will move basically one plane over the other. So, what we will get? We will get this particular one, the back one. So, this back one is still in this form, but the front one, this the above one, which is in the shaded portion. So, which is also moving in this direction. So, this is the shaded one top. So, this is basically the corresponding prism structure, and we have the corresponding C3 axis which is also passing through it, and since we have the perpendicular C2 axis also and sigma h groups are also there. So, therefore, the point group is D3H. So, this triangular face, the movement of this particular triangular face which is above the other one will giving rise to the corresponding trigonal prismatic geometry. So, what we have there, so how we get this structure, which is important, and how the binding is also changing. When we moving this, basically with this particular form we are moving. So, our chelation is also changing, that means where from this connectivity is going for these particular points. So, we get these particular points and how these chelations are there. So, these chelations are nothing but, since we have this particular D3H symmetry. So, one ligand will be here, second ligand will be here and the third ligand will be like this. So, this is the corresponding geometrical form for the tris chelate. So, if can also be from any compound, like it can be cobalt, tris ethylene diamine compound, which can remain in this particular form for this distortion. So, what about this particular other twist that we will see for this other type of distortion, and these two are therefore forming or going through the corresponding trigonal prismatic conformation. So, the trigonal prismatic conformation is there in both these two cases, but if we look at these things we can think of why they both have the trigonal prismatic conformation, but in one case the point group symmetry is D3H, but in the other case the point group symmetry is C2V. This is due to the connectivity of these vertices which are for this particular trigonal prismatic arrangement. So, the vertices are connected differently when they are symmetrically connected along the C3 axis. The point group what we are getting, what we have shown just now is D3H, but in other case the twisting is little bit different and we are leading to a lower symmetry point group and the point group is therefore there is C2V. So, how these two are coming, let us see. So, in this particular case when we get this, so this is the thing, this is the octahedral geometry and these are the bidentate chelation. If it is around cobalt, the cobalt is sitting over here. So, with that particular cobalt center, this is the bidentate chelation, one another bidentate chelation and this is the third bidentate chelation. And when along this C3 axis the movement is taking place, so we get the trigonal prismatic arrangement and this prismatic arrangement along these three edges which are parallel to the C3 axis. So, this is the C3 axis which is passing through this triangular plane and this triangular plane also connecting toward this, and this is going up and the other side is going down for the C3 axis, and symmetrically these three bidentate ligands are covering the C3 axis and we basically get that the corresponding geometry where we go for the other one. So, it is racemization is taking place for the movement from this particular form to the other form. But in case of the other type of twist, the rays of the twist, we get this particular conformation, that means we take this other axis, that means we take this one particular plane as this triangle and this is also the other triangle binding in this fashion, but these two binding are in this other form. So, this is not for this particular axis, because for this case we have 4 C3 axis and along one C3 axis we have shown the distortion if the movement is taking place for the other C3 axis which were there. So, for the other C3 axis which is taking place, that means this particular plane where we have this triangular plane where these two positions of this triangular plane are connected by this one ethylene diamine molecule and another triangular plane which is there for the connecting of these two groups are by this bidentate ligand, then only we can give rise to the corresponding symmetry of this is different compared to the previous one. And there also this, if the movement is continuous one, that means from the trigonal prismatic arrangement to anti-prismatic arrangement, that means this is moving further and that movement if it goes we get the other form. So, in these two cases what we get, these two forms, what we are able to get is that in one case how this racemization we can assess that due to this movement what we find for these molecules, the two structural arrangements are possible. So, this is viewing through one particular axis for this only, say, because the other one is from the other axis. This is not perpendicular to this plane, because we can have the other C3 axis are there, and along these other C3 axis we get the other twist. So, when it is showing from this is the Bellard twist, and from the other, which is the corresponding Redath twist, by taking the other C3 axis, which is also equally probable for the twisting. So, when we get this connectivity, that means the bidentate chelation is from this side and from this also and from this also. So, this is basically giving, that means if we move from top face to the down, this is in clockwise direction. So, the isomer is the delta isomer, but if we go for this one, that means if it is in the other direction from top to bottom, this is from top to bottom, this is the top face. So, this is on the other direction, that is in the anti-clockwise directions, which is therefore the lambda isomer. So, due to all these things, we are basically ending up with getting these two isomers nicely. So, this twisting basically giving rise to the corresponding two isomers, one is the delta isomer, another is the lambda isomer, and racemization thus takes place due to simple twisting, because in no point we basically go for the cleavage of this bidentate chelation remain intact for all these 6 positions, but some internal distortion, that means this particular connectivity is not very much fragile for this distortion, they remain it and they result it basically for the other form, which is the corresponding racemized form. So, that basically gives us for the corresponding racemization in the octahedral complexes, and then we just see that what type of reactions we can follow for the different electron transfers. So, the electron transfer reactions, what we know that they are basically responsible for the different types of redox reactions, and these redox reactions are basically responsible for electron transfer from one species to the other, and this particular is also responsible for the transfer from one side to the other. So, they all require the transfer of electrons, and when we see that this transfer of electrons can take place through the involvement of some species where this particular metal center we consider as M1 and the other one we are considering as M2. So, when they are reacting, they can be different also, that means one particular center can be a cobalt center and the other center can be a chromium center. So, if we see that this has a oxidation number of X plus and this has an oxidation number of Y plus. So, what is happening, therefore, the electron is moving from one to the other. That means, in this particular case, if we have the pair, that means if it is a cobalt in the +3 oxidation state, then this is one more higher oxidation state. So, it is a +2 oxidation state for. So, one electron oxidation will take place on this particular state. So, this is therefore a center where it can consider as a chromium center, which is going for one electron oxidation to a chromium 3 center. In a similar fashion, if this is the center where it is in the Y, that means if it is in the +3 state, it will be reduced to +2 state, that means it is Y plus and it will be Y minus 1 plus, that means it will follow some 1 electron reduction. So, in this particular case, what type of oxidation reduction can take place through this electron transfer is very important, not only for these different types of metal complexes, but also for biological system, because it is a very central process for many systems where we have the metallobiocides are responsible for this sort of electron transfer processes. So, we see here that how we get some of these electron transfer reactions apart from the transfer we get for the different types of ligand exchange. Ligand is moving from one metal center to the other, but in this particular case very first reactions which are much faster than ligand exchange can take place. In that particular case it may involve some ligand exchange, but sometimes not, and very important in biological processes which I just told you that it is also important for metalloenzymes, different cytochromes, the blue copper proteins and all, where very fast electron transfer reactions can take place from one protein site to the other. So, what we see here that for a particular type of redox reaction we can have two reaction mechanisms. One is the inner sphere mechanism, where we get a particular type of reaction requires formation of bridged bimetallic species and which results in ligand transfer at the same time. That means, if we can have a ligand such as that of the corresponding X, which can consider it as a X is there. So, X is the unique ligand and that unique ligand can bridge two metal centers. One is the corresponding case, it is can be a cobalt center or it can be a chromium center. So, if we get this species like that, if we have a cobalt X pentaamine compound, X pentaamine whole 5 2 plus, which is reacting with chromium H2O whole 6 2 plus with the presence of 5 water molecules in protonated form, that gives rise to the corresponding transfer of this X from here to here. So, how this is happening? So, this must grow through an intermediate where X is the typical bridging ligand. So, we must have this X, that means X should be our bridging ligand. So, in that particular case the ligand transfer is also taking place from one side to the other, that means it can move from the cobalt side to the chromium side. And another one, that means another type of mechanism what can take place over there is the outer sphere type of mechanism, where this sort of bridging is not required and there is direct transfer of electrons between the metal centers. So, metal centers are involved and there will be a direct transfer of electrons, and through a outer sphere mechanism, though inner sphere mechanism is not required, in inner sphere mechanism the bridging is important. So, we find that in outer sphere reaction mechanism, when this outer sphere reaction mechanism is taken place, that electron exchange can take place between two separate and full coordination spheres. It is readily identified when no ligand transfer occurs between these species. So, the bridging ligand is not involved for the transfer, and it is easier to identify when complexes are inert with respect to ligand substitution. That means, we are not allowing any kind of ligand substitution, but in case of inner sphere mechanism we see that bridging is taking place. That means, at the same time we have the corresponding ligand substitution reaction, but in case of outer sphere mechanism therefore, we do not have any kind of such ligand substitution reaction. So, in this particular case the Born-Oppenheimer approximation is applicable, and because the electrons are moving at a faster rate than the nuclei. So, nuclei cannot readjust themselves nicely. By that time electron will take place in a very fast way, and rate of the outer sphere reaction mechanism can take place is dependent on the product of the oxidant as well as the reductant and the corresponding K value, and the complexes reorganization can be considered as a separate step from the electron transfer. So, reorganization step is different one, it also takes some time to reorganize, or that is why it is also dependent on the corresponding rate of the reaction. And in biology it is this form, that means the outer sphere reaction mechanism is therefore useful, which is most often used for this type of electron transfer reaction. So, what we see there, that Marcus equation is also applicable in this kind of transfer, and electron transfer requires vibrational excited states, and the shape of the potential energy will determine the rate of the electron transfer. So, Marcus equation, it proposes one particular reaction rate which can tell us that what type of electron transfer can take place, and different thermodynamic and kinetic parameters can be derived by using this particular equation. And the theory which basically predicts and correlates the rate constant of the reaction. So, whenever we have a rate, we basically find that rate for this outer sphere mechanism, which can be considered as OSM, the rate for the outer sphere mechanism is dependent on the concentration of the oxidant into the concentration of the reductant. And this particular rate constant for the reaction, this can be considered as K12 for species 1 and species 2, and this particular rate we find that K12 is the electron self exchange rate constant of the reactants K11 and K12, and the equilibrium constant for the electron transfer reaction K. So, there is some equilibrium constant for the electron transfer K. So, this K multiplied by K11 and K12 will give rise to K1, which is the self exchange rate constant. So, self exchange rate constant can be determined by knowing this particular equation. So, the product of these two, this K11 and K22, reflects the intrinsic barrier to electron transfer, and K is a measure of the overall reaction free energy, that means delta G0. So, this basically tells us some idea that how this thing can be useful for the outer sphere mechanism. If we just see that these two species are involved for that particular outer sphere reaction, we find that this can go for the corresponding electron transfer. One is getting oxidized and other is getting reduced for this transfer. Similarly, the cobalt center as well as the ruthenium center can have, and this can go for the corresponding transfer of electron between these two. And in all these cases, the coordination environment is not changing, coordination environments are remaining intact, and we can have a corresponding solvent cage for these two. So, these two are basically trapped inside the solvent cage, and within that particular solvent cage the electron transfer is taking place, and from this we can basically get the corresponding delta G0 value depending upon the corresponding energy state for the reactants as well as the corresponding products. So, in this particular case, the reactions which are about 100 times faster than ligand exchange rate reaction, the coordination sphere remains the same, and what we just now told you, that the rate, that means this R value is dependent on the K and the concentration of A and B. So, this basically tells us that in this particular case there is something which can be considered as a tunneling mechanism. So, outer sphere mechanism, which is also true for biological electron transfer, a tunneling type of mechanism is operating for that biological electron transfer also. Thank you very much.